Okay, let's continue where we left off then. I guess I have to turn on the projector. We're talking about the client-server architecture. And this diagram on slide 12 illustrates it's one of the UML sequence diagrams where we got to last day, that illustrates the general sequence with which servers interact with, or a example sequence with which a server can interact with a couple of clients, okay? Illustrating the kinds of things that go on in a typical server and a typical client. This is just to remind you where we got to the other day. We also talked briefly about the fact that there are several alternative approaches. You don't have to use a client-server architecture. There are other ways of doing things. For example, as the bottom one point says, you can write data to a database and have some other program read from the database. That's another way of communicating. Or write to a file and have some other program read from a file. So that is another approach. But the client-server architecture has a lot of benefits, such as the ones on this slide. The work can be distributed among different machines. You can have different people get together or work independently as they want to develop the clients and servers. In fact, people who develop clients could be totally independent, competing company from people who develop servers. That's very common. You have multiple companies producing email readers, i.e. email clients, totally independent of the people who create the email servers. Okay? We have the option of saving data centrally on a server or distributing data to all of the clients, or both. Okay? So we have a lot of flexibility. There are pros and cons of each of those. Central data means we have a better management ability, and we can back up everything, using very, very, very rigorous safety precautions. But on the other hand, if we have a big disaster and we lose our server and by chance we also lose our backup, that's not very good, and therefore we lose all our data. So having data distributed to clients is another approach to data integrity, although the problem with that is that you might lose bits and pieces of your data. So you might lose a few client pieces of data, and that could cause a problem with your system. Like, well, gee, we've lost a few of our employees' pension records. Not all of them, but only a few. Well, that's too bad for those people, Probably you don't want to have that kind of thing happen. So depending on the requirements of your system, okay, you'll want to try different approaches to where you save the data. Okay. Now, I've already talked about a whole bunch of different client-server systems in passing. This slide number 15 just gives a list. So the World Wide Web is basically the largest client-server system out there. In some sense, you can consider it one system. It's got multiple servers and an absolutely incredible number of clients. And clients, while running, can connect to any of the servers anywhere on the internet at any time. So definitely a very big client-server system, a standardized architecture, standardized protocol, communication language, HTTP, plus a number of specialized languages, like there's a secure HTTP and FTP and so on, can also be used on the World Wide Web. The email system using Simple Mail Transfer Program, SMTP, Simple Mail Transfer Protocol, SMTP, is also another widely distributed client-server protocol and architecture, with many different clients and a few very well-known servers. The web has a few very well-known servers too, by the way, as I'm sure you know. Apache and Microsoft are two of the big dominant players there. Network file system. Well, there are a number of different standards here. Basically, the idea is on a local area network, sharing files. So the network file system was one of the earliest, and it's still one of the most robust, and was designed originally for Unix systems, so that basically you can run a Unix computer and look at files totally transparently. They're on some other computer, but they look as though they were on your computer, and you can work with them as if they were on your computer. So you have one file system that, instead of just being local to a disk, is spread over an entire corporate network. Okay? A network file system in general, then, is something which is not distributed around the world. It's within a local area network. But you have servers. In fact, each computer that has files that it is willing to let others access, other computers access, becomes a server, and any computer that wants to access other files becomes a server, becomes a client. Transaction processing systems are another major class of client-server system. Okay, so systems for airline reservations and banking and so on. Instant teller machines will use a client-server protocol where the machines themselves are clients and they communicate with servers. And usually the network's more complicated than that. For example, let's say I go to the Royal Bank machine that's up in the building in the corner, and it's a client, of course. It will connect to a server, which is the Royal Bank server. But if your bank happens to be some other bank, CIBC, then it will in turn connect to the CIBC. So you have another client-server interaction. And that illustrates one point, and that is the same computer, the same program even, can act as both a client and a server at the same time. And that's quite common. In fact, you can have programs that act simultaneously and always as client and server. See, client and server is a role. Okay? So I can be, at the same time, always a client, and at the same time, always willing to act as a server to other programs. And if you have that completely symmetrical pattern, where there's nothing central, and everybody can act as a central unit for some function, then what you have is what is called a peer-to-peer network. All of these programs are acting as peers. Okay, so Napster was an example of a system which had peer-to-peer attributes. And there are many other file-sharing protocols, some even more peer-to-peer than that. Remote display system. This computer right now that I'm using, okay, has a remote display mechanism set up so that the university computing services can look and see what's on this screen at all times. Okay, and they can connect to any of the podium computers anywhere in the University of Ottawa and take control with the keyboard and the mouse and do things. So if a professor says something's gone wrong with my computer, I can give them a call and they can take control. And so what happens is you have a server sitting in here, you have a client, and that client can connect to this server and say, send me all the output and let me have control as well. Anything I do will be reflected on the display here. Okay, that's a PC-based remote display mechanism. The granddaddy of all the remote display mechanisms is a client-server system called X Windows, which was originally developed for the Unix platform again. Unix pioneered a lot of these kinds of things because Unix computers were networked well before PC, Windows, Intel computers were. Communication systems such as telephone networks and so on. Okay, basically, anytime you make a telephone call these days, it's done, certainly in any community that's, well, I'd be surprised if anywhere in Canada we still have any of the older analog systems left. I mean, somebody can correct me if you put your hand up. They still exist somewhere?
Yeah, in my place.
Where's your place?
Gananoque, Ontario.
Gananoque. They still have an old analog box down there.
Phone lines only support 28.8 motors.
Wow. That's amazing. Okay, well anyway, okay, so they still exist. That's interesting. But for most of us, we're working on digital telephone exchanges now, and basically, except for the wire from your house into the telephone exchange, everything from then on is just a computer network. Okay, and so you have these central offices, as they're called, communicating, sending messages backwards and forwards to each other to control the switching of the messages and so on. Okay, and then they use tons and tons of protocols and tons of servers and clients to perform all that functionality. And then finally, database systems, okay? You have database programs which you fire up, and these database programs just sit there waiting for various clients to connect to do queries. And the typical, in the relational database model, they would query using the SQL language. And in fact, there are protocols now which allow clients to connect to different kinds of database, so-called open database connectivity. So you can have databases made by Oracle, and your client can do queries on those, and then you can switch to an SQL database that's, say, Microsoft or something like that, and you can also have clients that connect to those too. So client-server systems are ubiquitous, and you can't avoid using them. And as you know, as time goes on, we're going to have more and more systems developed this way. Okay, now let's go on and talk in a little bit more depth about the ways that clients and servers behave. We started talking about the way a server behaves, but this slide number 16, goes into that in a little bit more depth. And among the things that we'll see in this slide are the fact that on this diagram here, the top part above the dotted line shows effectively what goes on in the context of the thread. Remember we said that there's going to be threads, multi-threaded, okay? So you've got two kinds of threads in a server. You've got the one thread that is waiting for connections. The diagram here on the top is saying that the black dot says it starts up in waiting state. So it starts waiting, and then whenever a connection comes in, it starts it's waiting. It starts waiting, which means it's not actually listening for connections yet. Then it starts waiting for connections. Okay, when it's ready, it's now willing to take connections. At some point in time, it will accept a connection and continue waiting. And at some point in time, it might stop listening. It might say, I'm going to shut down for a while and not accept new connections because I'm doing some kind of maintenance. Okay? At the same time, we have, in parallel, any number of these threads at the bottom, below the dotted line, which say handling a connection. So when they're started, they start handling the connection, and they keep reacting to messages until the point comes when they decide to handle disconnection. This little circle with a dot in the middle of it says that's the end. Okay? And finally, the whole thing can end. You'll notice that the whole thing starts outside the big box with a dot and initializing. Then the whole thing starts. At the end, the whole thing can end. So this diagram you're seeing here, which shows the various steps that go on, which is also illustrated on the left-hand side of the slide textually, is what is called a state diagram. And there's another kind of UML diagram that we're going to study in depth later on in this course. Okay, and each of these little boxes is a state. So initializing is a state. At some point in time, the system is in the state where what it's doing is initializing. And then later on, it gets into a number of substates, different parts of it, different threads of it are doing different things in parallel. The dotted line means the stuff goes on in parallel. And effectively, we have to imagine that there's multiple cases of this thing down here. Okay? Questions? Okay, now let's talk about, we're going to talk about activities of the client, and then we're going to put it all together and just imagine all the multiple threads, okay, in a minute. Activities of a client. This is another UML diagram, and I used yet another type of diagram. It looks like a state diagram. In fact, it's very closely related to a state diagram. It's called an activity diagram, and it's illustrating the way a client will typically behave. Okay? First of all, a client's going to initialize. Every client, any program, whatever kind of program, will always do some things when it starts up. Okay? At some point in time, it will initiate a connection to a server. And then it decides to do two things at once. Okay? Most clients will do this. Not all. Some clients don't have user interaction. But most clients will, at one time, decide that they're going to have some interaction with the user. And in parallel with that, they're going to be communicating using another thread that is communicating with a server. And we talked about why this would have to be the case. Imagine that I have this over here is the one thread, the thread that's interacting with the user, and over here is the second thread, the thread that is communicating to the server. So you're the server. Okay? So this thread that's connecting to the server is expecting at any point in time it might receive a message. Okay? So it's listening and waiting eagerly for a message. You send a message, I've got it. I can do something. I can update my display. Okay? Now the user might be doing something. Okay? At the same time. So my user over here is typing away, is pulling down menus to look at things, is scrolling scroll bars to look at stuff. At any point in time, that message might come in from the server and cause information to be displayed on the screen. So I can't have my whole system sitting waiting for you. I've got to have a part of it sitting waiting for the server coming from the message, and I've got to have the other part sitting waiting for the user to type keys. And the order and sequence is going to be unpredictable. Which can come first? I don't know. So I've got to wait for both at once. And that's why I need to have the multi-threaded environment in the client. Okay? So we already had the multi-threaded environment in the server. I said in the server, I'm doing multiple things. I'm communicating with multiple clients at the same time, and I'm waiting for new clients to connect. So I've got, n plus m connections. One plus n connections. One waiting for new connections, and any number of waits on particular connected clients. In a client, I've normally got at least two. One waiting for the user, and one waiting for messages from the server. Okay? That's the normal approach. That's the approach that makes the programming easiest. There are trickier ways to do things with single threading, but we try to avoid them because they are tricky. Any questions about that? Okay. Notice just some little details inside these two threads. Okay, so the first thread says interact with the user, sending messages to the server as necessary. Okay, so this thread that is interacting with the user, when the user presses a button, there will be some quick response. That button will trigger some method to be invoked, and that method to be invoked might do some quick calculation, might change the display, and might send a message to the server if that is what is called for as part of the computation, and then return. Okay. Now you might say, well, there's delays during that going on. We don't want the user to experience delays, and that is absolutely true. Generally speaking, these interactions with the user, the response to them needs to be fast. Okay? And there might even be other threads that go on that continue to control the display and react to the user while computations are going on. So I'm showing this as one thread, but there could be more than one here. So the responses come in on the thread that's waiting on the server. The requests to the server generally are sent from the other thread. Okay? Another thing, by the way, that the second thread, the one that's waiting on the server, has to do is it has to handle situations where the network breaks down. Okay? So we're back over here dealing with the server, and all of a sudden you decide you're going to shut down. Okay? Or the network between us is severed. So I say, oh, I'm ready to detect that. I have an exception handler. I'm in a try-catch block. Okay? There's an exception that gets thrown by the operating system, and that gets propagated up into Java that says network down. Okay? So that's one of the things I have to do. I'm waiting for messages, but I'm also waiting for the breaking, okay, of the connection. When the connection is broken, then I'm going to also take some action. Typically, I would display on my user's screen, and my user would see that. My user might have been typing something, and then the user sees a message saying network unavailable, or maybe waiting to reconnect. Okay, maybe the response of the server thread is to say, oh, severed connection. Okay, maybe it's transitory, maybe it's temporary. I'm going to wait a few seconds and try and connect again. And if I can connect again successfully, then we've got another connection back again. Depending on the design of the system. Some systems will try and reconnect, others will not. And also, it might have been the server booted me off. I mean, it might not be a network breakage. It might be the server has said, I'm done for the day, shutting down permanently. Hopefully, it would have sent a message to say that before it actually severed the network. Or it might be the server saying, you client have been badly behaved, or you client have been hanging around too long, and you have to get your work done in a limited period of time. So we're going to just unilaterally kick you off. Any of those things have to be handled by this thread that's interacting with the server, and presumably they cause display, but whatever happens, the user should still be able to type and click the mouse. Okay? Questions? Let's put this all together again. Okay, what you're seeing on this diagram is another one of these sequence diagrams. Again, we'll talk in more depth about the syntax of them later on. But we have here an example of the client side and the server side, and all the different threads interacting in one particular scenario. Okay, so in this case, we've got our client side, and again, I'm going to act as a server over here. I'll just walk over there when I'm talking client. Okay, let's talk about server. Okay. So we have a wait for connections thread that's running, okay? And then we have wait for messages client A, wait for messages client B. Notice these boxes mean the lifespan, okay? So the wait for messages client A doesn't start right at the beginning. Wait for connections does. Wait for messages client A doesn't start right away. But wait for messages client B does. Maybe because this scenario has been going on for a while. And the top of the diagram is a point in time that we're showing what's been going on for a while. At the start of this scenario, client B is being connected. Okay. In fact, you'll notice that there's no interaction with client B all the way through this whole scenario. It's just sitting there connected. But notice there's I have a third kind of thread over on the server now. That's an interesting one. The third kind of thread is another user interaction thread. Up until now, I've been talking about servers as if they've got the one thread waiting for connections, one thread, and set of threads dealing with clients. But now I've got a user interaction thread on the server side. So any program can have a user interaction thread, and that can be useful for having an operator controlling what the server does. Okay? It works basically the same as the client's one. Okay? So let's just walk through this scenario. The first thing that happens, okay, is that I have got in my client, okay, it says client A there. Okay, client B is just sitting doing nothing, but client A is the one that's interactive. The first thing it's going to do, it says is create. Okay, but it's the thing that initiates that is the thread that is interacting with the user. So the user clicks some button, or types something, or does some kind of interaction whose response, as programmed, is to initiate some kind of operation that requires a connection to the server. Okay? The second horizontal line, connect. Okay? So there is then this message that says, send a message to the server to connect. Okay? Okay. Then we go back over to the server side. And on the server side, now we have something starting to happen. Okay? On the server side, we've got, we're going to create this thread, this big vertical box now starts. Okay, the life of this thread starts at this point. Okay, because the message came in from the client and our wait for connection said, okay, we need a new one. Create this thing. Okay. Now, dealing with this whole interaction, we've had 3 different threads involved, but now basically the wait for connections work is over. We've got this thread on this side, on the server side, that's waiting for messages. And over on the client side, we've got some things going on. So the next thing that happens over on the client side, okay, is the client says, the user's doing stuff. I've connected to a server. The user's pressing buttons to connect to a server. Maybe from the preferences, maybe, I don't know how it is, but there's different ways that the user can connect to a server. Sometimes it's just implicit. I click on a link on the web, and in 2 fell swoops, I'm connecting to a server, and I'm also requesting a document. Like the 2 requests are done effectively simultaneously. Okay? But if you look down here, send message is the next message that comes out from here. So now the user thread is again saying, okay, we're going to send a message to the server to do something, get some action for us. Okay? Well, go back to the server now, and that is picked up, this time, by the wait for messages thread. Okay, notice the first message was picked up by the wait for connections. This one is picked up by the wait for messages thread. The server is now going to take some action in response. It does some thinking, does some computation, and replies. Okay? It's going to reply. And that reply is going to go back not to the client's user interaction thread, but to the client's server interaction thread. Okay? Because that thread has been sitting there waiting for responses from the server for a while. And, okay, it's waiting. Message comes from the server. Okay, that message is dealt with, and it's going to say display reply. So it displays reply, and there might be some interaction on the side of the thread that's dealing with the user at that point in time for actually doing the display. Okay? And then the user now, okay, I'm continuing to work as a user. I see a message coming up on my screen. Ah, interesting. Okay, I take some reaction. Maybe it's a message that maybe it's an instant messaging program, and what I get is a message that says hi from some other user or something like that. I'm now going to respond. And so it says send message. Same sequence happens all over again. I send the message back to the server. The server does some computation, does a reply, and then so on and so forth. I'm not going to go back over there. Display reply, and then finally the server now, something interesting happens. The user may be planning to continue work, but all of a sudden I've got yet another thread now that kicks in. My server administrator is looking and saying, gee, there's some bad stuff going on here. There's some, serious breaches of security or something going on between this client and this server. I'm going to kill this client. Okay, so this server operator notices something strange going on and says kill. Okay, and that sends a message to our wait for messages client in the server, and then that sends a disconnect message back over to the client, and the client at the same time says display disconnect and kicks off. Okay? So that's a scenario we've walked through of interaction. Typically in these scenarios you have hundreds and hundreds of interactions backwards and forwards, maybe thousands, sometimes millions of interactions between a set of threads in a client-server system. Any questions about that? Okay, good. Well, hopefully you have a thorough understanding of that. You are going to be working in the lab with this. Some of you started last night on the Thursday lab. Others will be continuing to do that and over the next three lab sessions today, Monday and Tuesday. And then there will be a repeat of that pattern. The repeat of labs. The lab B continues. It has another iteration next week, because this is a big lab and takes 2 weeks plus to do. Let's talk about two classes of client-server system. There's the thin client system and the fat client system. Okay? Thin client systems are systems where we make the client as small as possible. The client basically has a small user interface, and almost all its work is respond to mouse clicks or typing and send messages immediately to the server, and that's it. And every now and then we get a message from the server, and all we do is display the results on the screen. Okay? So nothing but interpreting mouse clicks, sending messages to the server, and getting messages from the server and displaying results. No computation, no data storage, just the bare minimum that we can do. That is a thin client system. It's thin because all the fat stuff, all the work is going on in the server. Okay? An advantage of a thin client system like that is that the client is effectively a very small program, or should be if it's properly compiled and so on. There isn't much code there. And therefore what you can do is you can download that client very fast over the network. And in fact, the notion of applets in web pages was originally conceptualized as being primarily for thin clients, where there was not very much computation and data storage going on the client side, but maybe a little bit of sophisticated management of the UI, a little bit of fancy display, things which can't be directly done in HTML and so on, a little bit more liveness to it, but nevertheless primarily for thin clients that can be quickly downloaded. Okay? Then we have, on the contrary, fat client systems. Fat client systems are systems where most of the work goes on in the client. Okay? So in our client, we have our data storage and we have our computation. And the access to the server is quick messages to get stuff that it needs, like a quick database query, or a quick, maybe it's sending a message to some other user somewhere else. Maybe it's a game program. The work is on the desktop. The game, interactivity is there. All the computations, all the data storage, all the graphics is all there on the desktop. But we're sending our moves and our position to other players who we're playing against. Okay, The server is involved primarily with exchange of information with other players, but doesn't do the game playing actual work. Okay? So that's an example of a fat client system. We can illustrate this just diagrammatically, showing more work for heavy and less work for light. So A is a thin client at the top, and B is a fat client at the top. Okay? And one of the things that we have to do when we're designing systems is to decide, are we going to be thin client? Are we going to be fat client? Or are we going to be somewhere in between? You know, you can sometimes have systems where it's a little bit, you know, one, a little bit the other. That's a design decision. Part of the engineering process is making design decisions based on pros and cons, trade-off analysis. What's going to cost the least? What's going to use the most network bandwidth? Who thinks that thin client is going to use less? You know what network bandwidth is? Let's just talk about that for a second. Network bandwidth is the amount of traffic, the amount of communication you have over a network. Okay? How many people think that a thin client system will use less network bandwidth than a fat client system? How many people would guess that? A couple of people. How many people would guess that a fat client system would use less network bandwidth? Okay, a few more people. Well, the answer is there isn't an answer, because it depends on a lot of things. Okay, a thin client system can use relatively little bandwidth in some circumstances. Okay, if, for example, you know, we're displaying, so maybe it's a chess game, and we're displaying a board. Okay, and you know the computation of the game is going on in the server, let's say. But all we have to do to transmit is the moves. So there isn't an awful lot of bandwidth used there. In fact, whether it be thin client or fat client, it doesn't really matter in that case. So other situations would come into play. Sometimes the network bandwidth would be very heavy if you have a thin client, if we have to display graphics. If all the computation of the graphics is going on the server, we have to constantly display updated graphics. Gee, the thin client is going to have to, you know, be accepting transmission of all those things. Whereas if instead we can somehow compute the image right on the client, that saves all that transmission. Okay. Other times, it might be the case that a thin client ends up being a lot less work if, for example, we're doing some kind of complicated analysis where we want to fundamentally do computations that end up displaying data on the client but have to go and get information from all over the world, let's say. Okay. So if to get this data and display it on the client, I have to get data from all over the world. Okay, if I have a fat client that does all the computation of my display, then I'm going to have to be sending my messages out all over the world from the client to all kinds of different servers. And maybe my client is going to be on a modem connection or on a relatively low bandwidth connection in somebody's office. Whereas if I can put all of that connectivity work down on the central computer, which is connected to a big fiber optic cable, then you know that overall balances the bandwidth better. So there's tons and tons of individual choices that can be made and individual trade-offs depending on the needs and requirements of a particular system. Communication protocols. I mentioned to you the other day that the word protocol has the same general flavor as the notion of protocol in diplomacy. Okay, so it's a set of rules and a language for communicating. Okay, so the first thing is the language. The language are the messages that the client sends to the server, plus the messages the server sends to the client. Now, it might be that they actually use different languages. Okay. Typically, in a web browser, for example, the kind of things that the client sends to the server are get and post. So get a URL to display and post information in a form. Okay, those are two of the typical things that the client will send to the server. The server, on the other hand, is going to be sending HTML back. So they speak different languages. It's as if, I'm having a conversation with somebody and I'm speaking English and you're speaking back to me in French. Okay? But as long as we agree to do that, and we kind of get used to the weirdness of it in that case, it would work, right? You could imagine doing that. Okay? So you can have symmetric protocols where both speak the same language, or asymmetric protocols where the server behaves slightly differently than the client in terms of the language. So we have either one or two languages, and then that means that they're having a conversation. Message there, message back, message there, message back. But the sequence of messages is important. For example, when I come to meet somebody, I'll typically say hello, or something similar to that. Hi, or how are you? How's it going? Good day, mate. That kind of stuff, right? And the person will respond and say, fine, thanks. Or maybe they, just give you a stare and say, glad you're having a good day. Depending on, the message they want to convey back, But most people will respond with some nicety, How are you? Very well, thanks. I'm sick as a dog, but the protocol says I'm supposed to say very well, thanks, right? So protocols are important, and they allow us to, in this case, establish communication. And then the conversation will proceed. And the normal rules of human conversation are, I say something, you wait patiently, and then when there's a break or when there's a question, you communicate to me. And I wait patiently. And when there's a break in the conversation or a question, or I'm just too eager that I have to reply anyway and cut you off, I'll do that. Okay? Those are the rules of human conversation, and we try to minimize that cutting in and breaking in. But sometimes, if somebody's yabbing on and on, we have to do it. Or if something urgent's coming up, we have to do it. Okay? So that's all the protocol. And the protocol does include that kind of cutting off and breaking in under some circumstances. We know that some people have to do that sometimes. It's fine, The building's on fire. It's acceptable to yell fire in the middle of a conversation. You don't wait for the person to stop speaking. So that's part of the protocol too. Similar thing with communication protocols. There are rules, and many protocols, I send a message, and when you get it, you reply to that message. You acknowledge that you've got it quite often, or you send back some standard reply, or one of two possibilities, yes or no. Maybe it's a yes or no question. You send back yes or no. And I, on the other side of the communication protocol, are waiting, and I won't do anything until I get the reply. When I get the reply, you're waiting, and so it's my job now to send the next message. So taking turns is a standard part of this communication. But also, some protocols do allow for a certain amount of what's called asynchronous communication, in which case one message might be sent, and I send another, and I send another, and I send another, and I don't wait for replies. I'm willing to just keep sending messages, and whenever the replies come in, they come in. Okay? So maybe I send data when it's ready, and the server sits and kind of processes the replies, and when it's finished its computation, it'll send messages back. But that's fine, because as a client, I have two threads. One thread can be sending, and the other thread can be waiting and responding, and it doesn't really matter the sequence. The other thread can wait, and maybe, after half an hour, it starts getting the responses from the slow server. You'll notice, if you look closely, that in a web browser, we have some of this asynchronous stuff going on. Okay? I'm going to be firing off to my web server when I'm displaying a page with lots of graphics, a whole series of different GET requests. One for the main page, and then as soon as the main page comes in, I get a whole slew of embedded graphics, and maybe other stuff embedded too, and I'm going to start firing off requests maybe before I've got my full response to the main page, and then I'm going to start getting these little graphics coming in one after the other. The sequence might be the same sequence I requested them, but it might not be. They might come in a different order. Okay? And they might not all even be to the same place. Okay, they might be to different servers. The graphics might be coming from somewhere else. There's nothing wrong with that at all. They don't have to come from the same place. Okay? And so I do have this sort of protocol that says, I send a request, and yeah, I'm going to expect a reply, but I'm not going to wait for it. I will wait if it's the main page, but But you'll notice that I can start interacting with the main page even before all the graphics get in, right? And I can certainly press the stop button and do all kinds of other things and start sending another request even before my first request has come back. Okay, I can, if I do that in most web browsers, what will happen is it will cancel the first request. So lots of things can happen, and there's a bit of asynchronousness in a lot of these protocols. Together, all of these rules about the sequences and what's allowed to come after what, and the two languages, all taken together, are called the protocol. Okay? The rules of behavior and the languages are the protocol. And in this software engineering program, there is a course in protocols that you'll end up taking in fourth year. Even in the computer engineering program, you'll learn quite a bit about protocols as time goes on, but software engineering gets into them in a little bit more depth. Now, let's imagine that I am the developer of a client-server system. So now we're talking not the system and what it does, we're talking about what the software engineer does on slide 21. Okay, so I have to do a number of things. The first thing I have to think about, and maybe not necessarily always strictly in this order, but one of the key things I have to think about is I have to design my computational work. Whenever I'm doing any kind of design and programming, there's going to be algorithms, there's going to be data structures and stuff like that. So independent of whether it's a client-server system, I've got that to do. Another thing I have to do now in a distributed environment is decide how I'm going to distribute the work. So is it that client, is it thin client, and which pieces of the computation are going to go on which sides of the communication channel. So that's a new piece of work in a distributed system. The third thing I'm going to have to do is to design my protocol, the details of the set of messages that will be sent from either side and the mechanism for that I will agree on for backwards and forwards communication. And finally, I will design the mechanism for initializing my client, initializing my server, handling connections. What do I do when the network goes down or a server kicks me off, etc., etc. How am I going to send and receive messages? You know, what is the piece of code that's going to be involved in the waiting and receiving? What is the piece of code that's going to be involved in the sending? And finally, terminating. How do I gracefully terminate? And one way to terminate is to just quit the program, exit 0. I can do that, but preferably I will negotiate with my server if I'm connected. Goodbye. You know, part of the human protocol is to say bye, see you later, something like that. Good day, mate. You know, ciao. That's part of the standard human protocol for terminating, and computers tend to do the same thing. They tend to gracefully terminate. Because one of the reasons for that is that if my standard way of terminating was just to disappear, in a human context, you know, I'm in the middle of a conversation and suddenly I turn around and walk away. Gee, that leaves a lot of questions unanswered. Isn't that person mad at me? Is that person a complete moron? You know? Well, you know, so the negotiated termination communicates a lot. It says, you know, we're done in a friendly way, and nothing's gone wrong. The same thing with the computer. You'd like to know whether something's gone wrong or not on termination, because if you do ever get a situation where suddenly the network's severed, you want to display to the end user or the server administrator, the network went down. Okay? If clients can just quit without that nicety, the server says, oh, another client's gone, another client's gone, all my clients have quit, that's nice, great. And do nothing, right? Whereas what you want is when you see the sudden severing of communication, you want the server administrator to say, something's funny going on here. Everybody's abandoning ship all of a sudden. So let's try and do something about it. So there's important information in how the communication is terminated. You know, is it done nicely? Is it done rudely? And there's sometimes more than one way of doing it rudely. One way of doing it rudely is to yell, fire, and get out of there. But at least you've yelled fire. Okay? Another way is to turn your back and walk away. And that that typically means something else. So when you're doing the development of a client-server application, you've got to design all this stuff. And it's not simple to design. There's a lot of bits and pieces to think about there. Yeah, question?
What happens if, for example, power goes off at the client side?
The power goes off at the what side?
The client side.
The client side. Hey, power goes off at the client side. If you've got an uninterruptible power supply, nothing. Everything is fine. But assuming that the actual computer is also off, the server just sees that as severing of the network connection. And you know, server sees something strange has gone on, but they can't, the server usually, the networks are usually not sophisticated enough to distinguish whether it's power gone off or whether it's a severing of the network somewhere else on the network. I mean, you could design a network that would do that, but the standard communication mechanisms we have in Java won't distinguish between those two kinds of things. Okay, any other questions? So you can see we've got a bit of engineering to do to get all that stuff done. And one of the things we have to do the engineering, is to have a thorough understanding of the low-level technology available to us, the reusable technology at the lowest level. So we're going to talk about low-level reusable stuff like Internet Protocol, and then we're going to talk about reusable stuff that we've produced for this book and for this course, which is the Object Client Server framework, okay, which builds on top of this. But you have to understand the different layers. Okay, later on, when you take courses in network architecture, you'll understand that a lot of the time we think about 7 different layers of communication, from the physical layer all the way up to the application layer. We're not going to get into that today, but there are many different levels of abstraction and detail in which we can think about the communication going on. One of these levels is what is called Internet Protocol, otherwise known as IP. I'm sure that you've at least heard this term before. Internet Protocol is the way that messages are shipped around the Internet at a certain level of abstraction. The Internet Protocol is involved in routing messages from one computer to another. So what's really going on when a client is talking to a server is that that client sends a message out of its wires, and it's received by another piece of machinery somewhere down the tube, which may not be a computer, but it's typically a router or a switch or something, which is in some sense acting as a server, but its job is not to actually serve the response, but to forward the message on. And it knows, it has all kinds of mechanism built into it that says, well, if this is a destination address, I know how to route this message on, so eventually it gets to the destination. And so you might have a number of hops as the message is going down one set of wires to one box, which, as I say, could be a router, a switch, or perhaps a firewall computer. A number of things could be on the way. It routes the message on and on and on until finally it gets to the other end, which is the real server that you're trying to communicate to, or the real client if you're the server going back. Okay? So IP is involved in how these messages get shipped around the Internet, how the addressing scheme works so that the message gets to the right place, and the splitting up of messages into the little pieces. Because if I'm sending a big HTML file, I'm not going to send it as one big chunk. I break it up into little pieces, and each little piece is sent separately. And then they're reassembled when they get to the end. So each little piece is a little message that's sent and routed around the network. The pieces might even take different paths. Can happen. They might not arrive in the same order. They can get held up. One piece can get lost, and there's going to be requests to retransmit. Which brings us to the next level, the Transmission Control Protocol. Okay? Transmission Control Protocol, or TCP, is handling things at a bit of a high level, built on top of IP. And its job is to handle the connections. Okay, so when I establish a connection from client to server or server to client, that's TCP/IP's job to maintain that connection, to keep track of the connection, and when messages are going to be sent over that connection, it takes care of that, and it takes care of making sure that the messages are put back together again properly at the other end. Okay? So you often hear people talking about TCP/IP, and that is the combination of TCP and IP components of our network. And by the way, those in turn will run over other kinds of things. So they'll in turn run over such things as Ethernet for local area networks. So when you plug a network card into one of our jacks that are out in the first floor all over the place, or into your cable modem or DSL modem. That's effectively using the Ethernet protocol. And then there might be other types of networks. There is in fact, there's protocols used by the cable system to transmit in a certain direction from the cable's office to your cable modem and so on. So there's different kinds of modulation schemes. If it's a modem, there's one kind of scheme. So these messages at the lower level, below IP, get transmitted using all kinds of different schemes over the airwaves. Over the radio waves, there's a number of different schemes depending on whether you're using cellular connections, which are digital or analog, and so on and so forth. Okay? So IP is on top of all that, and TCP is on top of all that. So by the time we get to the TCP layer, we've got a well-established programmable mechanism which we can generically use anywhere on the internet, or not just on the internet, but also on intranets, INTRA, which means inside our corporate firewall. Okay? And there's even mechanisms available to what's called tunnel TCP/IP from one corporate network to another, okay? Or from your cable modem to inside a corporate or university network. The recent EduNet system has what's called a virtual private network system, which basically makes it look as though you're inside. So when you're connecting through that, it looks as though you're actually inside the university's firewall and so on. There's all kinds of mechanisms built in to this whole environment. And it's not the subject of this course, but you should build a familiarity with how things are going on, because when you have problems with networks and client-server communication, you want to have a vague idea of what the problems could be. You know, firewalls often cause problems with client-server systems, and we'll see some of the issues with ports and things in a few minutes. Any questions about those kinds of issues so far? As I said, just a brief gloss. This is not the subject of the course, but it's to give you a sense of what else you need to learn to do this kind of stuff. One of the things that we will need fundamentally in any client-server system that's on the internet, and by the way, this is internet. There has historically been other network architectures that use different mechanisms, and even in the internet, TCP is not the only way of doing things at this level. There's also a thing called UDP you might hear of. But in this course, we're going to be talking TCP. Okay, so in TCP/IP, each host, which basically means each computer, okay, or device that acts as a computer, such as a cell phone if it's internet enabled, or a PDA if it's internet enabled, or a switch or a router or whatever, has an IP address. Okay, this is a numeric address, and you can sometimes see these things showing up on websites instead of the alphabetic version. So, you know, they're numeric sequences, and you can look these up in the lab. One of the things you'll do is you'll look up the IP address of your thing. It's 4 numbers, each number from 0 to 255, separated by dots. Okay. Now, it turns out that we're running out of those addresses, and so they're changing the scheme a little bit. So that 4 number mechanism is called IP version 4. And we're migrating now to IP version 6 on most networks, which is a bit more sophisticated. But we don't have to worry about that in this course. So in addition to having an IP address, each internet-enabled device also has a name. And the name is for the human consumption. The name is so that you can say, I want to get the news from CNN.com, and I don't have to know the IP address of CNN.com. I just know the name of it. So I can type CNN.com, and there is a whole protocol out there, okay? There's a whole protocol with which your computer will say, somebody type CNN.com. I have no idea what this is, but I do know that I have a domain name system server that I can communicate with that will find out what the IP address of the CNN.com is. So I'm going to communicate with my DNS server. And it's another client-server system, okay? And there's a whole hierarchy of DNS servers all over the network, one for each level of the hierarchy. So at some point, I say to my local one, tell me CNN.com. And it will say, my local one will say, I don't know CNN.com. Nobody's accessed CNN.com recently. So I'm going to go out to the .com. And I'm going to find go to the .com server and get the IP address of CNN.com, and then that one's going to send it back to me. Now I know CNN.com's IP address is. Now I can use the numeric address to communicate directly to CNN.com. and then I send my message, and my routers will route it to the correct numeric place. Okay, so it's quite a sophisticated architecture, this. So each host has an IP address and a host name. Several servers can run on the same host. Okay, so CNN.com has multiple servers, in fact, multiple hosts. You know, it's much more sophisticated than just one computer serving your responses. But let's imagine that it's as simple as that. Multiple servers running on the same host. Each server has therefore got to have yet another identifier. And that identifier, which identifies the program that you want to interact with, is called a port. And these port numbers can run up to about 65,000. And there are standard port numbers for particular services. So the standard port for the web is 80, for example. And if you have a secondary web server, people tend to use 8080 as another, if you have two web servers running. That's one way of doing it. But you can actually pick any port number you feel like. Okay? Sometimes it's desirable to pick obscure port numbers because hackers are used to hacking in on certain port numbers, and if you use a strange one, then they don't know where to find it. But at the same time, your users don't know where to find it either. So the advantage of using a standard port number is that everybody knows, as soon as they know CNN.com, you don't have to type :80, the default. They say, oh, I'm going to go to :80. So the colon followed by the number in the URL is the port number. It says which program on the computer you want to communicate with. Okay, so in the lab this week, one of the things you'll be learning to do is to get servers running on different ports. Okay? By default, in the software for this book, in this course, it's using port 5555. I just picked that out of a hat. Okay? That could clash. There could be some other program running on that. But if there is, that's no problem. We can just change to another port number. And so one of the things you'll be doing is learning how to set your client and server up to communicate on a different port number. And that gives you some experience playing around with the system and changing the code a little bit to make it more flexible. Okay? Any questions? Okay, let's move then and talk about Java and how Java does some of this stuff, how Java works with some of these things. Okay, in Java we have a package called java.net. This has nothing to do with Microsoft's .NET stuff. It's just, which is, by the way, a whole other set of mechanisms for some of which has to do with setting up client-server systems. But the java.net package is a package that basically allows you to manage TCP/IP connections between applications. So building client-server systems or peer-to-peer systems, any kind of distributed system. We have to do a number of things, and the key classes that we have to worry about in Java, one is a class called server socket, and the other is a class called socket. Okay? The terminology here is that a socket is like the end of a connection, and I have a wire running between my two sockets on my two communicating programs. So on the server end I've got a socket, and on the client end I've got a socket. Okay? And the server socket acts a bit differently. Okay, the server socket, its fundamental job is to wait for connections coming in from anywhere. The regular socket, just without the server prefix, is the normal communication, either on the client end or on the server end, to send messages backwards and forwards on a connection. So server socket is to do with establishing connections. Regular socket, on both ends, is to do with communication once a connection has been established. So what a server has to do is this little expression here. It says server socket type, declare a variable of that type called server socket, and assign to that a new instance of server socket on a particular port. Okay, so this is an incantation for creating a server socket. And yeah, we have to say what the port is. Like we said that this will declare that anybody who tries to communicate with us, with this server, will have to try and connect to this particular port number. That's an int. Okay? And then, after this first expression, is executed, there's 2 lines shown here, but it's one expression ended by a semicolon. Once this is done, the server, if it will return a value, and there may be an exception thrown. So we have to surround this with other stuff like try-catch blocks, you'll see. But at this point in time, if this succeeds successfully without throwing any exception, we have a server running on a port, but it isn't yet accepting connections. Okay, it's sitting in a waiting state, ready to start accepting connections upon the initiation of maybe the operator of the server. Or maybe we do, in fact, immediately say the next line, which is, okay, declare a socket. I'm going to back up one little second there. This says new server socket port. Right. What I have to do is I typically put this second line in a loop, okay, because I typically want to accept more than one client. Okay, so typically the second line, expression here would be in a loop, because if I just have it immediately following, I'm only ever going to be able to start one client. So this line here says, okay, at some point in time, when a client tries to connect, I'm going to start a thing which I'm going to call client socket of type socket, and I'm going to assign to that the result of this expression. So in fact, I execute this expression, and this accept method will wait. It will sit and wait until a client message comes in over the network saying, please connect. And then this expression will end, and I end up with my client socket created, unless an exception is thrown. So first line says establish the server, but don't start waiting. I execute this expression, and it hangs effectively on the accept. Okay, this has got because it hangs on the accept, this has got to be in a loop, so I can continue doing in a thread, so I can continue doing other things, interacting with the user of the server, etc. Okay, if you don't completely understand that, take a look at the rest of the code that surrounds this in the Object Client Server framework. Okay. But are there any general questions at this point? So after finishing executing both of these lines, I have a server socket, which is my accepting connections from the outside world, and then I have a connection to a particular client. And hopefully I'm going to continue doing this in a loop, accepting connections from different clients over the course of time. When the client wants to connect to a server, it does something very similar to this second line. It will also create a thing, we're going to call it client socket here to show the symmetry, and it will assign, it will say new socket host port. This is the request to connect to a server on this host and on this port. And when this returns successfully with the result put in the variable client socket, we have a connection established. At that point in time, on the server side we have one of these things, and on the client side we have one of these things. They, from that point on, are basically symmetric. Either can send messages when it feels like, and either can receive message. Either has to be ready to receive messages. Okay? So aside from the fact that at the beginning the server has this mechanism of accepting connections, its job, the definition of a server is something that accepts connections. But once the connection is established, the communication can be totally symmetric. Either one can initiate the messages, either one ought to be ready to receive messages from the other. Okay? And they both use the same class called socket to do that. Question? Why there is no semicolon on what line? Right. So equals server socket equals new server socket port. This is because this is one expression. It wouldn't fit. It would run off the edge of the slide. Okay. It's just it just got split because you have 80 characters to work with on a regular screen, whereas I only have about 50 characters here to play with. So it's just to make the font bigger. But there's no, in Java, I could put each word on a separate line. It would still work. The expressions ended with a semicolon. So. By the way, if you do split lines, the standard practice is to indent the second line like this to make it clear to people you've done that. Okay. Okay, so I have my connection established. Both sides have a socket. They can communicate. Now I want to exchange information. Okay? To exchange information, I need an additional set of classes because I have to decide the kind of data that I'm going to be exchanging. Okay? It's all very well saying I'm going to be exchanging information, but what kind of information? Okay? Well, first of all, there are a set of classes called input stream and output stream. Okay, input stream is a class that has to do with data coming into me. Output stream is a class that has to do with data that I'm sending out. These act very much like system.in and system.out. Like if I'm communicating to the DOS or Unix terminal screen, same concept. And in fact, I can use sockets in exactly the same way. I can output to these things in fundamentally the same way. It's just as if it's a terminal screen. In fact, I can adapt a terminal-oriented program to work in a client-server way by using streams. They're very similar. These are found in java.io package. Okay? So they do with I.O. less than to do with networking. I.O. in general. And so the expression I would use is, first of all, I'm going to say to my client socket, okay, get an output stream on that socket and assign the result to a variable called output. This variable called output I can then use to transmit information. And to my client socket I will also say a get input stream. And I will assign the result of that to input, and that is where I expect to receive information from. Okay? Now, I've got my input and I've got my output. So I can communicate information using these. I can say output.write some message. If I do that, what I'm doing is I'm sending bytes. Bytes is the most primitive type of information I can transmit. It also can be more efficient, but it's less abstract, and so I have to do more fiddling with my communications. And if I want to receive information, I have the thread that sits and waits for communications from my server is going to execute this thing, input.read. As any read statement will do, it will hang and wait. So if I'm reading on my terminal, I'm in a loop and I'm waiting, right? And somebody has to type something and hit return, then the read statement ends. If I'm using system.in. Same thing with using an input stream on a network. Okay? That's why I have my thread set up, my client thread set up, sits and waits on the read statement in a loop. So each time I finish reading, I process, go around the loop and read again. It hangs on the read. Okay, so that's communicating using raw bytes. I can step up one, and I can instead use a thing called data input stream and data output stream instead of input stream and output stream. If I do that, I can do things like write double and read double, which means, or write integer, read integer, or float, whatever kind of data types I want. So I can communicate over this network using things that are a bit more abstract than just raw bytes. But if I do that, I better be prepared for my other end to know what's coming, right? If I'm communicating messages using read and write double, then the protocol, the language of communication, is going to be double values, okay? And so normally you probably don't do that. Most of the time, what you do in a protocol is use either bytes or strings, okay, which allow you to use Unicode to transmit, okay? Or, even beyond that, I can use object input stream, object output stream, and that allows me to communicate any object I want. So now, what I have to do is if I'm sending arbitrary objects over my network, arbitrary Java objects, then I have to make sure that in my client and in my server, I've got the same classes defined, right? Because if my poor server suddenly starts receiving an object of a class that isn't in its system, it's going to be at a loss to know what to do with it, right? So if I'm going to use something called if I'm going to use object streams, then both client and server, part of the protocol is they've got to have the right classes so they can communicate with those particular classes of objects. Okay? So I can actually send an instance of passenger, an instance of airline reservation, an instance of you name it, I can send it, including strings, because strings are objects. Okay? So I can send things at a high level of abstraction with all of my instance variables all filled in, and they all get nicely received at the other end. Okay? Can somebody think of a disadvantage of using... We know the advantage of using object input stream, object output stream. The advantage is abstraction. The advantage is we're working at the high level. We don't have to interpret bytes. What is a disadvantage of working, aside from the fact that we have to have the classes in both sides? But beyond that, what is a more stronger disadvantage of doing that? Yeah?
We have to cast everything coming in.
Well, yeah, that... there could be the issue there. It says message equals input read object. And so, yes, you'd have to do some casting there. That's true. But that's not so much of it. As long as your protocol is established. If you know that the next message you're going to receive is an airline reservation, because that's the sequence, it's what's got to be next, then you can do that. Of course, if the client violates the rules of protocol, then you end up with some problems. So you have to make sure that your reliability of both sides is very up to the task. There's another problem. Can anybody think of that? Yeah?
Well, there's some overhead.
There is some overhead. That's right. There's some overhead of creating these objects. But in some sense, if I'm transmitting bytes representing an airline reservation, I'm going to have to write my code manually to put those things together and generate an object called a constructor anyway. But you're right, the overhead of using these is going to be a little bit more than probably if I handcrafted something maximally efficient to do that. Anybody, I'll get back to you if anybody think of any other disadvantage? Okay, you again then?
Well, if you send your output stream, if the server isn't in Java, can it still understand?
Right, okay. So it kind of constrains my server to be in Java because it's going to be getting these messages that are coded in a special way that Java understands to build objects at the other end of the network. Absolutely, and that kind of constrains my developers, and that leads very closely to another disadvantage that I'm just thinking about, and that is, anybody got it? That is that. Go ahead.
You were expecting a particular type of object, and they may not send you that.
Well, that relates to the point I made earlier on. But the key is it's evolution. If I make a change to my class hierarchy or my class structure on the server, the client has got to be updated at the same time, so it's got the same classes. And if I add an instance variable on one end, I've got to add it on the other end at the same time. Otherwise, I end up with lots of incompatibility problems. Okay? So we have that problem. So there are big advantages in terms of abstraction and speed of programming, but there are also some disadvantages too. And so this is another one of these engineering decisions that you have to make. Are you going to go with detailed bytes? Are you going to go with objects? Or in the middle, we've got strings. Okay, now the object client server framework we'll be talking about, which is the topic we'll start on next day, does in fact use objects. It's called Object Client Server Framework for a reason. It will allow you to communicate with objects. In this course and in the example application, we're going to be primarily using strings, because that's intermediate. Strings is built into Java. Strings is not going to change in its structure. We can communicate with strings, and they will be understood. We still have to break apart our strings and do some processing of them a little bit, but it's not as bad as using bytes. Okay? So we'll leave it there today, and we'll pick up starting with the Object Client Server Framework next time.